So, good evening. Welcome to the eighth problem solving session for the course Environmental Remediation of Contaminated Sites. So, I am one of the TA for this course. My name is Asma Parveen and I am a PhD scholar from IIT Kanpur. And the course instructor is Professor Bhanu Prakash Valanki from Civil Engineering Department, IIT Roorkee. So, we have covered materials till week 8. 4 weeks are left. So in week 8, we have, I think, materials related to solidification and stabilization. And in that, we will see few numericals based on TCLP approach. So we have started the course with introduction about the various solid waste management rules, and then we have seen the hazardous waste management rules 2016, and we have tried to briefly go through that rules, and then we have gone to no, uh, to finding the risk related to the various pollutants, where we have find out the carcinogenic risk and non-carcinogenic pollutant risk, and then we have moved to the various methods for remediation of the contaminated site, where we have seen the first method as pump and treat, and then we have seen that pump and treat is feasible and cost effective when the pollutant is present only in the aqueous phase, which is generally not the real life case or scenario, because the pollutant generally is distributed in different phases. And then we have seen that if the pollutant is partitioned between the gaseous phase or aqueous phase, or if it is being partitioned between the solid phase and uh, liquid phase, or if it is soaked on the solid sediments or soil, or if it is some non-aqueous phase liquid, then pump and treat method is not effective, because we have already seen that we have calculated retardation factor, and with the absorption of the pollutant on the soil, the retardation factor increases by many folds, and also if there is some non-aqueous phase liquid, then again the retardation factor increases. So we have seen that pump and treat method is not suitable for all those aquifers contaminated with non-aqueous phase liquid, or if the pollutant is sorbed on the soil or sediments, and also present in the aqueous phase. Then we have moved to the second method, which was uh, reactive permeable barriers, where we have seen that we have seen a case study in US, in Utah, where a reactive permeable barrier was used to remediate a contaminated site with uranium. So in reactive permeable barrier, we have seen that some reactive materials are installed in these layers, and water flows through these layers, and the pollutant gets removed from the water by different mechanisms like sorption or redox chemistry, or there can be precipitation. And then we have seen few numericals based on the design of the reactive permeable barriers, where we have tried to find out the thickness of the reactive permeable barrier required based on the type of pollutant and the concentration of the pollutant. And then we have moved to the third method, which was natural attenuation. So in natural attenuation, what happens is that degradation of the pollutants takes place with the help of microbes, and generally the natural attenuation is present in the aquifers. But to remediate a particular type of pollutants, some modification in the terms of operating condition, or some genetically modified microbes can be introduced into the aquifer to remediate that site or remove the pollutant. So again, we have seen two types of remediation. The one was destructive, and another was non-destructive. So in destructive attenuation, we have seen that the pollutant is totally destroyed and converted to some other compound, but in non-destructive, pollutant is not converted to other compounds, rather it is sorbed or removed by other mechanisms, and its original phase or original form is present after removal also. And then we have solved few numericals based on these also. Natural attenuation, I think we have solved two numericals where we have seen two different cases. One was where only diffusion was taking place, and another was one where both diffusion and advection was taking place, and we had to find out the, I think, rate constant related to that problem. And then we have moved to fourth technique for remediation, that is solidification and stabilization. So solidification and stabilization has started in the previous week, where we have seen that in solidification we try to compact the hazardous waste in some material so that leachability of pollutants decreases. And then we have seen few concepts related to solidification and stabilization. And in the current week, that is week 8, we will try to solve few numericals based on the concept of solidification and stabilization. But first, let's go to the lecture slides briefly. So this is the first lecture which was on introduction to solidification and stabilization. So here we have seen that cement is being used to solidify the waste materials like fly ash, where the leachability reduces a lot. So solidification or stabilization treatment typically involves mixing a binding agent into the contaminated media or waste. So if you will add some binding agent, then this binding agent will bind the contaminants and hence the leachability of the contaminant will reduce. So this can be done both in situ and ex situ. So in situ, what happens? The binder agent is directly injected into the contaminated media, and in ex situ, what happens? That the contaminated soil or the material are excavated, and then it is mixed mechanically with some binding agent, and then uh, solidification is done. So there are next is a vitrification. So it is two types of stabilization and solidification can be done. One by using cementitious material, and the other can be done by vitrification, where a heat source like electric current or some direct fired kiln is used. So what happens when we will heat a material, then at some depending on the temperature for that material, the soil or pollutant will uh, melt, and by increasing the temperature at such a high temperature, many of the pollutants gets immobile, as it is converted from the more mobile phase to the less mobile phase, or it's get traps into the silica phase. So through pyrolysis, we can immobilize most inorganics and destroy organic pollutants. So pyrolysis is the thermochemical conversion in absence of oxygen. So during pyrolysis, what happens that since it is generally done at more than 350 degrees centigrade, so the organic pollutants will get destroyed at such high temperature, and most of the organics, especially the heavy metals, gets immobile. But there are few types of waste where the leachability of the heavy metals can increase on pyrolyzing. So what happens is that when the soil gets melted and it's converted into some vitrified glass and crystalline mass which have very low leachability. So the organic pyrolysis combustion products captured by an off-gas treatment system. So if we are pyrolyzing a waste, then we should have proper treatment for the gaseous product which comes out during pyrolysis. So in pyrolysis, we have three products. First is the charge, which is the solid residue. Second is the bio oil, which is the volatile compound in the gaseous phase, which need to be condensed and separated out. And the third phase is the gaseous phase where it can have some calorific value because it has methane and CO, and but this gaseous products should need to be treated before disposal or before use. So next is the type of site and contaminants treated by solidification and stabilization. So these are the sites like manufacturing gas plants or wood preserving sites, industrial and municipal landfills, plating facilities, oil refineries, all these can be treated by solidification and stabilization. So the type of pollutants which can be remediated here is the heavy metals like lead, arsenic and chromium, or some organic contaminants like petroleum product. So next is the effectiveness. So here we can see that the square boxes shows demonstrated effectiveness, a triangle shows no expected effectiveness, and the circle shows potential effectiveness. So here we can see that for dioxin and furans, which are very toxic to humans and other living organisms, it can be effectively immobile or stabilized by using solidification and stabilization. So now this is the different control treatment technologies which can be used to remediate different sites. So next is the case study where site was remediated in Florida using stabilization and solidification. Please go through this case study in the lecture videos. Okay, let's move. Okay, let's go to the next lecture. So let's discuss about the different contaminant reactions which takes place. So either it can be precipitation. Here example is given that if the lead is present and if hydroxide is given, like pH will be increased, then lead will precipitate out as lead hydroxide. Again, this will be it will be a reversible reaction. So it can also go from solidified lead hydroxide to the aqueous phase of the lead. So next reaction is the complexes. So lead can react with ligands like hydroxide or chloride, and it can form different complexes, and these complexes are generally soluble and they can contribute to a pollutant in the water. So next reaction can be adsorption, where the pollutant can adsorb on some media. Redox reaction can take place, that is oxidation reduction can take place. And next is the incorporated within the matrix. So suppose there is some silica and there are some voids created. So in those voids, the pollutant can get trapped and then can be removed out. So next is the transport mechanism. So advection can takes place or also diffusion can take place, and we will try to solve numericals based on the advection and diffusion of pollutants in solidification and stabilization. Next we'll discuss about leachability. So next is the diffusion of contaminant through solidified form. So here equation is derived when there will be sorption and when there will be advection and diffusion. So the leachability can be find out by using the TCLP approach. So TCLP is a toxicity characteristic leaching procedure test in which the pollutant or the waste is mixed with the extractant solution in 1 is to 20 ratio, and it is rotated for 24 hours, and then the concentration of the pollutant is find out. So the insolidification and stabilization, the approach is to pass the TCLP test, that is the concentration of all the pollutants in the extracted aqueous phase should be less than the TCLP limit. Suppose for cadmium the TCLP limit is 1 ppm. So in the waste we have which we have performed the TCLP test, so the concentration of cadmium should be less than 1 ppm. So here two approaches can be done. First is the pH. So for each heavy metal or each pollutant, there will be a pH at which the leachability will be least. But there can be different types of pollutants present in the waste. So we have to take the optimum pH at which the concentration of almost all the heavy metals is minimum. Next is we can add some binder like cement in which the um, waste can be binded up and made into blocks, and in this way also, since it is being binded by the cement, the leachability of heavy metals will reduce. So these are the calculations which we'll use to solve the numericals based on finding the fractions for different for stabilization of waste using cement. So again, fraction of binders. So the fraction of binders, admixture, water and waste. So we will try to solve numerical based on these approach. So we'll discuss these there. And next is the TCLP based example. So here a numerical is solved. So we will also try to solve a numerical based on this approach. So now let's directly go to the questions. So So the first question is, which of the following contaminants can be effectively remediated through solidification and stabilization? So we have four options. First option is halogenated volatile, B is metal, C is radioactive material, or D none of the above. So we have to select the option which shows that the contaminants which can be effectively remediated through solidification and stabilization. So I'll give you all 4 minutes. Just take your time, write the option in the chat box, and then we will discuss. So, 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 the type of the type of pollutant which is can be effectively remediated through solidification and stabilization is B, heavy metals, and C, radioactive materials. So heavy metals, it can be stabilized or its mobility can be reduced by binding with the binding agents, and also radioactive materials leachability or spread can also reduce by binding with binding agents. So B and C are the correct answer. Now let's move to the question number 4. So first and second question, these are two numericals, so we will try to solve at the end. So question number 4 is, which of the following statement is or are correct with respect to diffusion? So the first option is, the greater the effective diffusion coefficient, the higher the mass flux attributable to diffusion. Option B is, a reduced surface area results in increased diffusion. C is, decreasing the effective diffusion coefficient leads to higher diffusion. Or D, an increased surface area results in highest mass flux due to diffusion. So again, I will give you all 4 minutes. Just take your time, write your option in the chat box, and then we will discuss. So let's see which of the following are the correct option. So first is the greater the effective diffusion coefficient, the higher the mass flux attributable to diffusion. So diffusion flux is directly proportional to the diffusion coefficient. So if the diffusion coefficient will be greater, then the mass flux will also be higher. So first option is correct. Next is a reduced surface area results in increased diffusion. So this is not correct because we know that if there will be more and higher surface area, then there will be more diffusion. And if the surface area will be less, so the uh, area which will be available for the pollutant to be in contact with the water will be lesser. So there will be lesser diffusion. And option C, that decreasing the effective diffusion coefficient leads to higher diffusion. So this is not correct. And the third last option, an increased surface area results in higher mass flux due to diffusion. So this is correct. So A and D, these two are the correct option. Now let's move to the next question. So the question is, in solidification slash stabilization, if the leachate flow rate significantly rises due to a rainstorm, the concentration of contaminants in the leachate will A, first decreases then increases, B, decrease, C, remains constant, or D, none of the above. So again, I will give you 4 minutes. Just take your time and write the option you think correct in the chat box, and then we will discuss. So A is not the correct answer. That if there will be a rainstorm, then there will be a huge, there will be the uh, high volume of water which will come in contact with the pollutant, and this water will not have sufficient retention time, or the contact time with the pollutant will be very very less, so the concentration of the contaminant will decrease. So B is the correct answer. So if the flow will be less, then the contact time between the pollutant and the water will be high, and the concentration of the pollutant will be high in the water. But if the flow will be very high because of the rain, then the contact time will decrease, and that's why the concentration of the contaminant in the water will decrease. So B is the correct answer. Now let's move to the next question. So this is a numerical type question. So the question is, in solidification and stabilization, consider a system designed to minimize TCLP concentration. It's given that at the design pH, if ANC of cement is 14.2 milliequivalent per gram, and acid neutralization capacity of waste is minus 1.5 milliequivalent per gram, and acid neutralization capacity of water is 0. Water to cement ratio is given, and the acid neutralization capacity of mixture is given, and we have to assume that there is no moisture content of waste for hydration is available. So we have to find out the fraction of cement which will be required. So I will give you 5 minutes to solve this question, and then we will see how to solve this. Please write the value which you are getting in the chat box. So we have been given the acid neutralization capacity of the cement, waste and water. So our first equation will be, what is given? We know that what is the water to cement ratio. So fraction of water to fraction of cement is known, 0.37. Next equation, we know that fraction of water, cement and waste, that will be equal to 1. So fraction of cement plus fraction of water plus fraction of cement, waste, all these one will be equal to 1. And we need one more equation because we have three unknown, that is FC, FW and FS. So equation 3 will be ANC of mixture. We will equate with the ANC of mixture. So fraction of cement into acid neutralization capacity of the cement plus fraction of water into acid neutralization capacity of water plus fraction of waste into acid neutralization capacity of waste. All these will be equal to ANC of mixture, which is 2 milliequivalent per gram. So we have fraction of cement into acid neutralization capacity of cement, that is 14.2 FC, and acid neutralization capacity of water is 0. So Fs is minus 1.5. So minus 1.5 into Fs equals to 2. So we have three equations. Fw by Fc is equal to 0.37. Second equation is Fc plus Fw plus Fs is 1. And the third equation is 14.2 Fc minus 1.5 Fs is equal to 2. So by simultaneously solving all these three equations, we will get the value of Fs, Fw and Fc. So let's see what we are getting. So on solving, we are getting Fc as 0.215 and Fs is 0.705. So we have to find out the fraction of cement. So that will be fraction of cement is equal to 0.21. So this is the correct answer. So I hope this question is clear to you all. So now let's move to the next question. So again, it is a numerical type question. So the question is, a site contaminated with arsenic is to be treated by X2 solidification or stabilization at a SS facility. So we have been given distance of solidification stabilization facility is 40 kilometers from the site. Hydraulic excavation cost is given. Depth of the excavation is given. Area of the contaminated site is given. Cost of hauling and truck volume is given. So we have to find out the sum of excavation and transportation cost in million rupees, round off to 2 decimal. So again, I will give you 5 minutes. Please try to solve this question and write the value which you are getting. And then we will try to solve. So let's see how to solve this question. So we have been given volume of the soil. Okay, so we'll find out the volume of the soil. So let's write everything which is given. Depth which will be excavated. It is 40 centimeter. We have been given the area of contaminated site. It is given as 4 into zero point 0.6 kilometer square. Okay, it's better to convert into meters, so we'll convert it later. So we have been given the cost of hauling and we have been given the excavation cost. So first we'll find out the volume of soil which needs to be excavated. So that will be equal to the area into depth. So we have a area of 4 into zero point 0.6. It is in kilometer square. So answer is 8.2. No, answer is not 8.2 million Indian rupees. So okay, let's see how to solve this. What is the correct answer? So the volume of soil to be excavated will be area into depth. So to convert kilometer square to meter square, we will multiply by 10 raised to power 6. And then we have the depth as 40 centimeters. So again, to convert it into meter, we will divide by 400. So it will be 0.4. So the value which we are getting is so this much meter cube. So next thing which we will find is we will find out the excavation cost, because excavation cost is given uh, in rupees per meter cube. So it is 6 rupees. So 6 rupees per meter cube multiplied by 96, this much meter cube. So this much will be uh, okay. So it is coming out to be 5.76 million rupees. Next, we will find out the number of trips which will be required. So volume of truck is 8 meter cube. So we will divide the total volume of the soil to be excavated by the volume of the truck. So this will give us the number of trips for transportation. So this is the total volume divided by 8 meter cube. So this much is the number of trips required. And next we have been given the transportation cost, or the cost of hauling is rupees 8 per kilometer. So we will find out the transportation cost. It will be the cost per kilometer into distance into number of trips. So we have cost per kilometer is 8 rupees per kilometer. Distance is given as 40 kilometer and number of trips is this much. 1,20,000 trips are required. So all these after
It's just
calculation we sorry.
so I'm saying that this distance is 40 kilometers, so the trucks will go and come back also, no? So the rates will not be there for coming back.
Okay.
But
That should be included, but that is not here in the question. I think the cost of hauling has included both because it is not written that the cost will be for one way or the two way. So the cost of hauling is for
we
one
will not
trip
take the
from
second.
the contaminated site to that facility and then returning back to the contaminated site.
Yeah, so it is included in one. So
Yeah,
eight
yeah,
eight rupees.
yeah. If it was not included, then it should
Okay,
have
okay,
been
fine.
mentioned in the question.
It is to be multiplied by two. Yeah, understood.
Okay. So this we will get the transportation cost as 38.4 million rupees. So the question asks us to find out the sum of excavation and transportation cost. So the total cost will be sum of all these two. So we have excavation cost as 5.76 million rupees and 38.4 is the transportation cost. So adding these two, we will get 44.16 million rupees as the total cost. So this is the final answer. Okay, now let's move to the next question. So the question is, which of the following is not a technique or method to use or apply solidification or stabilization? First is cementous matrix formation, B vitrification, C pump and treat, or D pyrolysis. So we have to find out a technique which is not used in solidification or stabilization. So again, I'll give you 4 minutes. Just take your time and write the option in the chat box and then we will discuss. So the correct answer is pump and treat. Cementous matrix formation is used in solidification and stabilization. Next is the vitrification, where high temperature waste is heated at high temperature. And option D, where pyrolysis is used to destroy the organic contaminants. So only pump and treat, this is a separate method for remediation of the contaminated sites. So now let's move to the next question. So the question is, which of the following outcomes are not desired from the process of stabilization? A. Decrease in solubility of the contaminant. B. Increase in mobility of the contaminant. C. Decrease in mobility of the contaminant. Or D. Decrease in toxicity of the contaminant. Again, I will give you 2 minutes. Just take your time and write the correct option in the chat box, and then we will discuss. So the outcomes which are not desired for the process of stabilization is increase in mobility of the contaminant. So B is the correct answer. So the first option, that decrease in solubility of the contaminant. So in solidification and stabilization, we want that the solubility of the contaminant should decrease. Next, increase in mobility of the contaminant. We In solidification and stabilization, we decrease the mobility of the contaminant. So C is correct as per solidification and stabilization. And the last step, that decrease in toxicity of the contaminant. So this is also done in stabilization. So B is the non-desirable outcome of the stabilization. So now let's move to the next question. So the question is, the process of solidification involves change in the physical properties of the hazardous waste, while stabilization refers to change in the chemical properties of the hazardous waste. So we have to say whether this statement is correct or not. So again, I'll give you 2 minutes. Just take your time, write the option in the chat box, and then we will discuss. So this statement is correct that solidification involves change in the physical properties, but in stabilization there is changes in the chemical properties of the waste. So A is the correct answer. Let's move to the next question. So the question is, consider a site contaminated with lead undergoing treatment through solidification and stabilization. Key parameters include the length and direction of diffusion is 0.4 meter, total volume of treated material is given, total concentration of lead in treated material is given, and the time after disposal of treated material is given. Leachate flow contacting treated material is given. Observed diffusibility for lead in waste is given. Groundwater flow approaching disposal area is given. And for the analysis, it is assumed that only diffusion is taking place and all other transport mechanism are ignored. So given that the system had not yet reached equilibrium, the concentration of lead in leachate will be. So we have to find out the concentration of the lead in leachate by assuming that equilibrium has not been reached. So again, I'll give you 5 minutes. Please try to solve this question and write the option you are getting, and then we will see how to solve this. Okay, let's see how to solve this question. So we have been given, so first write down whatever is given. Okay. So first let us write the formula to find out the concentration of lead in leachate when equilibrium has not been reached. So the concentration in leachate is given as, so M net is the total concentration of the lead in treated material. T is the diffusivity for lead. L is the length which is given, length in the direction of diffusion. QL is the flow of the leachate, and small t is the time. So let's write everything which is given. So M naught, that is the total concentration of the lead in the treated material, is 1700 gram per meter cube. Sorry. So this is the concentration. So we will find out the total mass by multiplying with the volume of the treated material, which is 34 meter cube. So we will get the overall mass as 5.78 into 10 raised power 4 gram. So here M naught is the total concentration of the lead in the material. So we have been given D as the diffusivity for lead in the waste is given as 2.8 into 10 raised power minus 14 a meter square per second. It is 10 raised power minus 14. So we have QL, that is the flow rate for the leachate, is 12 meter cube per year. So we will convert everything into SI units. So we will convert it into meter cube per second. So 12 divided by 365 days, 24 hours, 60 minutes, 60 seconds. So after solving this, we are getting the leachate flow rate as 3.805 into 10 raised power minus 7 meter cube per second. So capital L, that is the length and the direction of diffusion, is given as 0.4 meter, and small t, that is the time after disposal of the treated material, is 80 days. Small t is 80 days. Again we will convert these days into seconds. So 80 into 24 into 60 into 60. So it's coming out to be 6.912 into 10 raised per plus 6 seconds. So we have got everything, M naught, D, QL, L and T. Now we just have to put in the formula. So let me change the slide. So the concentration of lead in the leachate PL will be given as M naught So M naught is 5.78 into 10 raised power 4. QL is 3.805 into 10 raised power minus 7. L is 0.4. D was given as 2.8 into 10 raised power minus 14 divided by pi, and time in seconds was 6.912 into 10 raised power 6. This raised to the power of zero point 0.5 means under root. So on solving, we will get the concentration of lead in the leachate. So final answer we are getting as 13.637 milligram per liter. So we have converted everything into SI units. So the final unit of will be for lead concentration will be milligram per liter. So I hope this question is clear. Now let's move to the next question. So this is the last question. So the second part for this question is if the lead concentration in the groundwater approaching the disposal area is zero point 0.2 milligram per liter, the resulting lead concentration in the water after mixing is. So this question is continuation of the previous question. In the previous question, we have find out the concentration of the leachate, and now we have a concentration of lead in the leachate. Now it is given that if suppose we have some leachate concentration in the groundwater, then after mixing of this groundwater with leachate, what will be the final concentration of the lead in the mixed water? So let me write the concentration of lead in leachate. It was 13.637 milligram per liter. So this question is very simple. If we have already find out the concentration of the lead in the leachate, so it is a very simple mass balance question. So I'll request you to please try to solve this question and write the value which you are getting. Okay, no problem. So here what we have done is like we have converted all the values which were given into SI units. Like we have find out the mass in gram. We have find out the leachate flow rate into meter cube per second as it was given in meter cube per year. We have converted the time in seconds as it was given in days. We have not done any calculation here. We have just converted the everything which was given in SI units. Okay. So then we have put all the values into the equation to find out the concentration of the lead in the leachate. Now let's see. So here we can. So here we have to find out the concentration of the lead in the water after mixing. So we can use a very simple equation, that is the flow rate of the leachate, concentration of the lead in the leachate. No, 6.915 is not the correct answer. Plus flow rate of the groundwater, concentration of lead in groundwater. This will be equal to the overall flow rate of the mixing water into concentration of lead in the mixing water. So we know QL, leachate to flow rate is given. We have already calculated the concentration of the lead in the leachate. We know the groundwater flow rate. Concentration of lead in groundwater is given as 0.2 milligram per liter. So the flow rate for the mix will be the sum of the flow rate of leachate and groundwater. That will be 12 plus groundwater flow rate is 1000 meter cube per year. And we have to find out the concentration of the mix. So again, I'll request you to redo the calculation and then write the value which you are getting. So here we do not need to do any conversion of the units, because if QL is in meter cube per year on left hand side, then it can also should be in meter cube per year on the right hand side. So without doing any conversion, we can easily find out the concentration of the lead in the mixing water. So I will give you 2 to 3 minutes. Please do the calculation and write the value which you are getting. Yes, 0.359 is the correct answer. So we have the flow rate for leachate as 12 meter cube per year. Concentration of lead in leachate we have already calculated as 13.637. Groundwater flow rate is 1000 meter cube per year. Concentration of lead in groundwater is 0.2 milligram per liter. Flow rate of the mix will be 1000 plus 12 into the concentration of lead in mix we have to find out. So this will be meter cube per year. So the concentration of the lead in mixture will be, so we just have to solve this question, solve this equation. Coming out to be 0.359 milligram per liter. So this is the concentration of the lead in the mixed water. So these were the questions based on week 8. I hope all the questions are clear to you all. So if you have any doubt, then you can ask or we can end the session here. Okay, thank you so much for joining. Have a nice day. We'll meet on next Sunday from 6 to 8 p.m. Thank you.